we'll start with the last talk of the day. We have Xavier Gómez Mont from CIMAT, who will talk about multiplication of the Jacobian algebra and hypersurfaces.
Okay, thank you. I'd like to thank the organizers for organizing such a nice meeting, and also I would like to take the occasion to thank Professor Griffiths, because reading his books and his articles, I have obtained much of my geometric intuition, so thank you very much for working so hard. And my talk is a relation between algebra and topology, and the main point is going to be some polarization, some bilinear forms. And so the algebraic setting is the following. We have a German holomorphic function with an isolated singularity. We have the Jacobian ideal generated by the partial derivatives of the function. And this is the Jacobian ring. It is a finite dimensional ring. And this ring also can be obtained from n+1 holomorphic differential forms modulo df wedge omega n. So this is another way to obtain a module. This is the Jacobian module, which has the same dimension as the Jacobian ring, and so there is an isomorphism which depends on the coordinates. And so we will denote by A, and there's a wonderful formula which is the following. So we take multiplication in the algebra A, and then we take this linear map from holomorphic functions into the complex numbers, which is 1 over 2 pi I to the n+1, and this is the integral over this cycle. This is the cycle where the norm of the functions is equal to epsilon of g, and then we put in the denominator f0 fn, and this set. So this over here is a closed differential form, and so it does not, this integral does not depend on the epsilon, and so it gives rise to a function. So if g is in the Jacobian ideal, then L of g is equal to 0 by Stokes' theorem. One applies Stokes' theorem into this formula. And really the fundamental thing of the map L is that the Hessian of f, which is the determinant of the matrix of second derivatives, is equal to the degree, which is a positive number. So this ring is a wonderful ring in the sense that it has a minimal ideal, a non-zero minimal ideal, which is one-dimensional, which plays the role of the dual to the maximal ideal. And so, but so one obtains this Grothendieck's non-degenerate bilinear form. Given it, so it comes from multiplication, and then we apply this linear function. It gives a non-degenerate bilinear form in this Jacobian algebra A. Now we're going to do multiplication by f in the algebra A. So multiplication by f is an impotent map, and we have the Jordan block type of the map. As we know from our linear algebra courses, we have this Jordan block decomposition, and so we are going to represent it in this form. So this means that this one over here is a block of size 4, so another block of size 4, then another block of size 7, and so we make this decomposition. And so the annihilator of f is these beginning terms, the beginning. So this means that if I apply f, I go to 0. So this I view as a pyramid. And then the f is you move to the right. So if you are on the extreme of the pyramid and you say you move, then you fall off the pyramid, right? And so now the primitive classes corresponds to the first part of the pyramid. And so in that sense, there is a bijection between primitive classes and the annihilator, because one of them is the beginning of the pyramid and the other is the end of the pyramid. And so, and this induces this is called the weight filtration. So the weight filtration means the following. You put in this, so you center the pyramid, in the middle all these strings, and you center, and then the ones over here you call omega 0, I mean omega minus m, omega minus m plus 1. You put the center in omega 0, and then you finish with omega m0, and by construction it has a symmetry because of this pyramidal structure. This I learned from one of first articles, but this geometric picture is my picture of this. So now, so we have these primitive classes, and so now one may choose a Jordan basing ordering them according to the weight. So this means that we begin with the basis over here, and then we complete the basis over here. But see, the thing is that if here we take omega 0, omega 1, omega 2, omega 3, then when you come over here, you put f omega 1, f omega 2, f omega 3, and then you put the new ones. And then this one, you put f square of this one, f of these ones, and then the new ones. And so you can be factoring the f's in this in this way. And now we choose this basis, and if we look at the matrix expression of this Grothendieck residue using this basis, it looks like this. So what this means is the following. See, if I take an element which is close here to the end of the pyramid, and I take another guy which, so if I take a guy here and I do the product with this one, then this one has a lot of f. And so with this one, if it's close here, I take inverse of f here, and then I push the f's, and then I push the guy off the pyramid. So if you're here close to the end of the pyramid, if you do product with someone who has enough steps previous, then you push the other guy. And so this becomes in the fact that in this basis, the matrix expression of the bilinear form is of this form. Now, here this suggests something which is the following: is to take the grading according to the weight filtration of this Jacobian module. So it is not anymore the Jacobian module. It's a vector space of the same dimension, but you're taking the grading, and then you can consider the bilinear form induced in the graded, which corresponds to taking the same matrix that we had before, but putting zeros underneath. So the trick of doing this grading thing is getting rid of these stars over here, and then one can do the following trick. So now this bilinear form in the graded module has the following trick, that you take a guy over here and a guy over here, and then so see here, if you take this, if you are in the primitive pieces, what you do is the following: is you move all the way to the end, and then you apply the bilinear form. That's what this is saying over here. See, you take primitive terms, so this term is going to be orthogonal to everybody except these guys. And so what you do, you get a non-degenerate bilinear form on the primitive pieces by doing, you take two elements over here, and so you push all the way, and then you do this Grothendieck duality. And so this means that there is a repetitive structure in this bilinear form in the graded Jacobian module, which is given by elements in this primitive form from this primitive thing. Now, for me, it's strange that there's the even and the odd. So this means this. So there are like two pyramids, one inside the other, because this is a degree 2 map. So if you have something which has degree 6 or -6, -4, -2, and then it's increasing by the construction we made, but then even and odd don't have to pair off, and so there are like two pyramids, and so one of them you can take the even one and the odd ones. So there are two structures, and so this repetitive bilinear structure means the following thing, is that in this graded module you have a direct, orthogonal direct sum decomposition, where here you have the even ones and here you have the odd ones, and then the even ones, these terms over here, correspond to the ones in the middle of the pyramid. So this means that the ones which are here in the middle ones, they don't get paired off with anyone. And then the ones which are here on the sides, then they get paired off. And so here it depends whether you're even or odd, is only the ones which are here in the middle. And so this bilinear form has this expression that these are the ones which are in the middle of the pyramid, and then the other ones you get a 1, and then you get a 2, and then you get a 3. And since I'm going to be interested in a moment when I make this thing over the real numbers in this a signature. So all these terms over here will give signature 0, so the only significant contribution to the signature of the bilinear form are going to be these terms in the middle. All these get cancelled out. So there is this repetitive structure. Now I'm also going to be interested not only in this Grothendieck residue, but in another form, which is first you multiply by f, and then you apply an element and an element. So instead of this formula which I mentioned before, this Grothendieck formula, you can play the following trick. So instead of doing this G and H, you multiply here with an f, or with an f squared, or with an f cubed. So this gives different bilinear forms. So there's not only one bilinear form, but there are a series of bilinear forms which correspond to multiplication by f in these terms. And so if you do this, then what happens is that since one is multiplying by f, everything which is in the annihilator of f, this bilinear form is going to be degenerate over here. So you get rid of these terms, you divide by the annihilator of f, and now you get a new bilinear form. But then the primitive structure, you can get the composition of the graded module associated to this module, and so you obtain it from the same primitive pieces. But before, here we had S0, S2, S4, and now over here we have S1, S3, S5, and if we do F squared, then we get S2, S4, so in that sense, one can obtain from this primitive decomposition not only the pieces of the original bilinear form, but for the bilinear forms. And so here, this is some questions I like to ask myself, is what's the meaning of this vector space, which is this graded sum of these graded pieces, and what are the meaning of these bilinear forms, the geometric meaning of the bilinear forms. And then this is motivated for the case over the real numbers, where we have a real analytic function which has an algebraically isolated singularity, when we can define the real Jacobian algebra using real analytic functions instead of holomorphic functions. And the same formula will give us a non-degenerate bilinear form. and then it has a sign, there's a signature. And so the question is, what is the meaning of the primitive forms in this case, and what is the meaning of the signature of this bilinear form in the primitive pieces overall? Because there is this theorem of Arnold that says that if sigma f is the signature of the real Grothendieck bilinear form on the real Jacobian algebra, then the Euler characteristic of the real Milnor fiber, which is this fiber f minus 1 equal to plus or minus epsilon, then you can compute the information contained in the signature is the Euler characteristic. But then we have broken up this signature into a lot of pieces with a repetitive structure. So, this question is the one which is motivating what I'm saying, what I'm trying to understand. Now, this other part was the algebraic setting. Now, here comes the topological setting. The map F restricted to a suitable neighborhood of 0 outside of 0 is a locally trivial fiber bundle with fiber, the Milnor fiber, which is homotopically a bouquet of n-dimensional spheres, and the only interesting homology group is this one. And so this bundle may be completed over 0. We saw better pictures than mine in Pablo's lecture. So anyway, so we have this vibration, we have this monodromy map, and then the monodromy map is a map which goes from the cohomology to the cohomology. We're going to decompose the monodromy map into its semi-simple and its unipotent part. And then from this monodromy map, we have the generalized eigenvalue decomposition. By the monodromy theorem, these are roots of unity. And then the unipotent part of the monodromy keeps invariant the decomposition. And so we have these maps. And then we define this n, the n operator, which is the logarithm of the unipotent part, which is this matrix. And since this is an nilpotent thing, this is only a finite sum. And so we have this n. Now, we're going to introduce a non-degenerate bilinear form in this vanishing cohomology, and the way one does this is the following. You compactify this, so the function, since it has an isolated singularity, you can make a change of coordinates so that it's given by a polynomial of sufficiently high degree, so that at infinity it has a nice behavior. And so you compactify into a projective variety, and here you consider coproduct in the middle cohomology, which will be a minus n symmetric form depending on the dimension. It is symmetric or antisymmetric. The monodromy map is an automorphism of this bilinear form, and this n is an antisymmetric operator. So we're going to play the same trick we played with the algebra A. So the algebra A had Grothendieck residue, and it had multiplication by f. Now we're going to define a non-degenerate bilinear form in vanishing cohomology, and the way one does this is on the generalized one eigenspace. One takes this coproduct on this extension y, but one puts an n. You apply an n. Before I applied an f, now I am applying the n. And then in all the eigenvalues different from 1, then it's coproduct. So this is something which comes from coproduct of a compactification, and is independent of the compactification that we chose. And then this Hn will be a direct sum decomposition, or an orthogonal direct sum decomposition, and this vanishing cohomology, what one is killing in the compactification is the eigenvalues corresponding to the eigenvectors corresponding to the eigenvalue 1. And so this is a polarization on vanishing cohomology. It's symmetric. If S is symmetric, then this one is antisymmetric. If this is antisymmetric, then this is symmetric. So this bilinear form is a little strange in the sense that it has an orthogonal decomposition. In one part is symmetric and in the other part is antisymmetric. In the algebraic case, it was always symmetric. Here, it's symmetric on one part and antisymmetric in another part. Now, we repeat the same procedure that we said before. So we construct another pyramid, the nilpotent map acting on vanishing cohomology by considering the Jordan blocks restricted to one of these eigenvalues. And so we construct another pyramid for each of these lambdas. For each eigenvalue, we can get one of these. So we can consider also the annihilator of n. We can consider the primitive classes. And then, now, here comes something very interesting. So, Pablo spoke about the monodromy. So you go around the singularity and you have this monodromy map. Now, so you have the eigenvalues, roots of unity. Now, you don't want only to go around the singularity. You want to go towards the singularity and see the behavior of the things when you go to the singularity. So, for example, the function t to the 1/2 and t to the 3/2 has the same monodromy problem, that when you go around once, you multiply by -1. But the thing is that there is this stronger, t is stronger than t to the 3/2. So in that sense, the difference between the eigenvalues and the spectrum is taking into consideration this thing of you want to approach the singularity. So the spectrum, so we're going, so the spectrum consists in the choice of logarithms of the eigenvalues of the monodromy. Now, we do not do the choosing. The choosing is done by the function. And so one has to figure out how does the function knows what's the logarithm it chooses. So here, if I take lambda, one of these eigenspaces, and I take lambda equal to e to the 2 pi alpha, then the spectrum will be choices of alpha, alpha plus 1, alpha plus 2, alpha plus 3, and the n operator here is the choice. So if I have a block of size 2 with respect to the n, then the spectrum will have choose alpha and alpha plus 1, and then the n lifts to the spectrum. And the Jordan block structure of the n in these parts in vanishing cohomology lifts into chains. So the spectrums are joined together by chains by means of this topological n. And now, since we have this bilinear form that we define in vanishing cohomology, it turns out that if you take lambda and mu, if lambda is different from lambda bar, they are orthogonal. So it's an orthogonal decomposition with respect to the eigenvalue thing. So lambda and lambda bar are the only ones which are interacting. And so there is a relation between the Jordan block decomposition of the n in here and the Jordan block decomposition of the n over here. And so when you lift this to the spectrum, then also they will correspond. The spectral values which are corresponding to the eigenvalue lambda and lambda conjugate are also related. There's this relation. Now, here comes, so that was the algebra, the topology. Now, how do you relate the algebra and the topology? So this is this Preschool Map. So the Preschool Map is a wonderful map, which is the array residue. So you take a function, g, and you consider the differential form g dc0 up to dcn. And then you divide by df. I'm going to explain how you do this division. So you do this division, and then it gives you I'm sorry, this should be cohomology. It gives you a cohomology class. So the thing is the following: given a section, given a holomorphic function in the ambient space, then there is this procedure of fixing a t, and then so you take this fiber V sub t, and now you take a homology class. You take a homology class in the fiber Vt, and then you do like you do in Cauchy's formula. You put a circle around, so a circle in the normal bundle, and then you move around, and so this gives an n+1 cycle, which does not contain where the poles where the poles are f minus t, and then you define the residue, and so given a function g, it gives rise to a section of the vector bundle, which over every point is the cohomology class of the fiber v sub t. So given any function, so there's a map which goes from functions to sections of the cohomology bundle by means of this formula, and then these sections, these are monovalued holomorphic sections. You can expand them according to Malgrange in fractional Laurent series expansion with coefficients in the eigenspaces of a vanishing cohomology. So this section can be expanded, and here you put t to the alpha j plus n appears, and these a alpha j's of t, these are multi-valued, these are flat sections of the cohomology bundle, but they are multi-valued, but exactly the multi-valuedness of the flat section gets cancelled out by the multi-valuedness of this factor, and so you get these terms, and the principal term of this expansion, so this is the first term which is non-zero, this is called the principal term, and the coefficient of this SG is the order of the and this what this says is what, when you go to zero, when you're approaching zero, then this term is the principal term, the principal term in the expansion. So now, so this induces a filtration in the set of functions by saying that the order of the function is bigger than or equal to alpha if the principal term begins in terms bigger than or equal to alpha. Now, there are some sections which we consider as trivial sections. These are the ones which are written in the form df over eta, because when I took this form and I divided by df, so you can cancel this df over here, and so these sections are, you take an n form, you restrict the n form to this complex n-dimensional variety, and this gives you this cohomology class. So you consider these sections as trivial. And so this B filtration on omega n+1 will induce an F filtration. So this is in the mixed Hodge structure of this algebra. This is the Hodge filtration. This is the Hodge filtration. and so the thing is the following. You say that S of G belongs to this F alpha if there is an eta in such a way that you can modify the G with df exterior eta and lower the order of the differential, and then you say that G is primitive if it is minimal in its class. Now, and so this gives this Hodge filtration in the algebra. The spectral numbers are exactly the points where the Hodge filtration jumps. That's how one obtains the spectral values, is in this way. And then there is this wonderful theorem of Parshenko that says the following thing, which is the one which relates multiplication with F. So you take one of these n+1 differential forms, be a primitive form, and then you multiply it by f of omega. And so the claim is that f of omega is not any more primitive. See, f of omega, if you do this expansion, since so if you take s of f omega, multiplication by f, when you pull it out, it goes as multiplication by t, because we are restricting to the fiber. We're restricting, but the function is constant on the fiber, so the multiplication by f in the algebra converts into multiplication by t. So in that sense, in the expansion, you would only multiply the expansion by t. But the thing is that this f of omega is not primitive anymore. You can get rid of the leading term, and the way you get rid of the leading term is the following: this omega, since you can find an eta in such a way that d of eta is omega, and so you take this eta, you make it exterior with df. So these are of this trivial, the ones I mentioned, and so you take f of omega minus df of eta, and you have diminished and so this theorem of Barshenko, this lemma of Barshenko says that if A alpha is the principal part of S of omega, then the principal part of f of omega, because this is 0 in the Jacobian algebra, is going to be n. And so here's where the n is coming in. The principal term, when you multiply by f in the algebra, it corresponds to multiplication by n in the leading term of the expansion due to this Barshenko lemma. So the result we have is the following. So we are interested in understanding this bilinear form. And so this bilinear form consists of two additive terms. The dominant one is a topological one, which is this one. And then there is another one, which is geometric, and it represents a non-topological binding of two n-Jordan chains in cohomology to one f-Jordan chain in the algebra. So let me explain this in an example. So here we have multiplication by f in the algebra. And so what we're claiming is that you have a chain in the A algebra, but then this chain will be broken up when you send it into the cohomology into two chains, one chain over here and then one piece, because we are going to break, you're going to get rid of this arrow. And so this happens because the following thing, no? So here you take the omega and you take its primitive form. And so this corresponds to this guy over here. Now, you start applying the f, and then you look at the principal part, the n, and then you apply the f, and then you get the n. But then it happens when you come to this point that you expected so this means that if you took the n, here you are in the annihilator of n, and so you get off, you go off, and so you begin here in another part of the chain, and so that's binding of two n chains in this algebra. And so the claim is that there is a new bilinear form which is concentrated in the annihilator of n divided by the annihilator of f, which is this geometric non-topological part. And so let me do an example. If we consider this function xy, x5 plus x, so this has this Miller number 19, and here is the eigenvalues, roots of unity. And here is the points in the spectrum. Now, you choose eigenvectors Sj corresponding to each eigenvalue, to each point in the spectrum. And so here you have this, an orthogonal direct sum, this S1 with the S19, S2 with it. So you have this symmetric orthogonal decomposition of this bilinear form in cohomology. And now you choose holomorphic functions in the ring in such a way that its principal part is exactly given equal to this. So you have these h's, and now when you do multiplication, so it happens something like this. So you have f of h1, and then it is f of h1, then it only has these three terms, 17, 18, 19. F of h2 is this one, so it has this term over here. F of h3 has this, and all the other ones in multiplication by f increases by 1, but there is no more terms over here. F of hj is equal to 0 on all of these. So if one looks at this residue bilinear form, it will have this expression over here. So this one has this expression. In this case of curves, irreducible curves in two variables, the n is identically equal to 0. So the topological part would be the 0 bilinear form, but nevertheless, in this, when you consider this bilinear form, it is a bilinear form of rank 2, n is equal to 0, f squared is equal to 0, but f multiplication by f is not 0. And so the Jordan block decomposition in the algebra looks at this form, and then this is the cohomology of the thing. And now, why I arrived at this problem is because it's some relation with vector fields to understand singularities. So we take a germ of a holomorphic function with an isolated singularity, and we consider the germs of holomorphic vector fields tangent to the singular variety. Then, let me see. So let me show you the formula. So here is this Arnold result I showed before, but let me show you the formula. So this is this is a previous result I have with Luis Giraldo and Mardesi, which says the following thing. We have a formula to compute the index of the vector field on X on the positive and negative part of the Milnor fiber. And so we have a formula here that uses some bilinear form of the same kind that I have been explaining before. And then there is plus some constant. And so this constant is independent of the vector field. It only depends on the hypersurface. And then we computed this hypersurface, and it turned out that this was the following. For positive values of the Milnor fiber, this is for the case of even number of variables, and even, this one is the sum of this signature of these bilinear forms in the primitive part, when we multiply with f to the m. And then in the negative part, then it is minus 1 to the m, the signature. So since this is coming from an index of vector fields, is something which is topological. And so this constant over here turned out to be topological. So what we're trying to understand is why these terms appear here. And so to understand this in the real case, we extended them to the complex numbers, and that's what I explained to you. And we have not yet finished our research to understand why these formulas appear over the real numbers and why these are the normalizing constant in this formula. So thank you for your attention.
Are there any questions?
If you take, say, isolated surface singularities, then frequently when you look at the versal deformation and look at the representation of the fundamental group of the parameter space minus the discriminant, you tend to get affine viable groups. Is that part of your story? So it's not just one monodromy transformation, but it's a whole vowel group, of which the one you're looking at is the product of the generators, the longest root. How does that fit in?
So you're saying like taking a morphification of the function, so as to create several critical points, and then this will be critical points of order 1, and then the monodromy will be just going around all the critical points at once. Now
That's just the topological one.
That's the topological one.
Yeah.
But see the thing here of as I mentioned, of the spectrum is that you get the spectrum when you approach the singularity. So if you open the singularities, then in principle you wouldn't know to which singularity. So in this sense, this is also related to the following thing, is to the speed at which these homology groups are opening up. So when you take, when you do this morphification of the function, then you have the parameter, and so you have some curves which are, so the morphification depends on the t, and so the critical points are moving in as curves. Now, the thing is the following, which is I think is the point over here. These are called polar curves. And so, but the polar curves, they may not be irreducible. See, if they are irreducible, it means that the critical points of the morphification are all going at the same speed. But if you have different irreducible components, then it might happen that the critical points are approaching at a different speed. So in this sense, in this vector field approach, because we have tried, when having a vector field tangent to this singular variety, is to push the vector field to a morphification. And so in that sense, there is not all the homology groups, not all the vanishing homology groups are the same. There are ones which have a bigger value than the others, and I think this is related to this Puiseux expansion, say, of the curves, the speed at which these homology groups are vanishing. And actually, my conjecture on how these things are related is the following. When you're over the complex numbers, all homology groups are in the end. In the end homology. When you're over the real numbers, it's more interesting because you have different homology groups. So if you have the speed of vanishing is not the same, then you have a flag you can take into consideration the speed of vanishing. So you can take Euler characteristic taking into consideration the speed of vanishing of the homology groups. So this gives some finer Euler characteristics which are taking into consideration speed of vanishing, which I think is related to these flags in homology.
Is there another question? Okay, so let's thank Javier again. We will see him tomorrow at 9 a.m. if I am not mistaken.
The fundamental group of the complement is generated by
So you're going to get a curve which is going to have several irreducible components. So the question is the following: how can you compute when t is equal to 0, which are the Morse index of the vector field, of the gradient of the morphification, and this will give you information of which are the homology groups which are leaving.